Today's topic is need for high impedance busbar protection. In the last lecture, we have seen the differential protection of busbars, and we have also seen how a CT behaves in the differential scheme, and we have also developed equivalent circuit of a current transformer, a CT. And we have also seen that a saturated CT will result in mal-operation of the differential scheme for external faults, because your differential scheme should not operate or should not detect external faults. It is actually meant for only internal faults. But if a CT is saturated, then it may result in false alarm because of external faults. So in the last lectures, we have seen how to model a saturated CT, and we have seen how saturated CTs result in detection of external faults, which gives a false alarm. In today's class, we will go through a simple mechanism how to overcome this problem of saturated CT and this false operation of your external faults. So there is a scheme which is used in power systems called as high impedance busbar protection, which is generally used to counter this problem of saturation of CTs. So in today's class, we will see this high impedance busbar protection, why it is used, and we will also see how this works in removing the false alarms due to external faults which happen because of saturation of CTs. So now let us suppose there is, we have seen this, we have seen in the last lecture that we do have a 3-feeder system. Let us suppose we do have a 3-feeder system. 2 incoming feeders are there. One is carrying 10 kiloamperes, the other one is carrying 20 kiloamperes, and there is an outgoing feeder of 30 kiloamperes, let us suppose. And each one is, right, this is A, this is B, and this is C. These are the CTs which are placed on these feeders. Now these two will sum up . Now let us assume this particular circuit. Okay, so under normal operation, these two will provide you 10 kiloamperes and 20 kiloamperes, and this E is being fed to the load through this feeder number C with 30,000 amperes. So now let us suppose an external fault of 30,000 amperes has occurred on bus bar in this 3-feeder. Now let us assume that this CT has been saturated, while these are not saturated, they are operating normally. And we have, in the last class itself, we have developed the equivalent circuit of a CT, right? And let us assume first of all, let me draw the equivalent circuit of the CT. Right, so this is IP by N, this is primary current by transformation ratio, this is RP, this is XP. These do represent the primary winding impedance, and this is magnetizing impedance, and these, RP dash and XP dash refer to the secondary, and these are RS and XS. These do represent the secondary circuit impedance, and this current, it will be divided into, one is secondary current, the other one is your magnetizing current. This is the equivalent circuit which we have developed for a CT. In case of saturation, this magnetizing circuit is considered to be shorted, right? So now I'll ignore the leakage reactances. Generally, these two will be neglected, and we will redraw the circuit now. See, This is the circuit which I have been discussing. See, this is here 2 incoming feeders, 10 kiloamperes and 20 kiloamperes. This is your outgoing feeder, 30 kiloamperes. Series CT1 and CT2 and CT3, A, B, C denotion. Now, see, they have been chosen with this CT ratio. So automatically this will listen. See, this is the current, right? So automatically it must ideally carry 10 amperes of current. But since it has been saturated, now assuming that it is having only 4 amperes. See, 4 amperes due to onset of saturation, which is less than its actual value. Whereas the primary side, these are not saturated. So 10,000 amperes with 3000 by 1 transformation ratio, they are carrying 3.33 and 6.66. Now this combined, this is 10 amperes. Ideally, it must carry 10 amperes. So there is no difference between these two. So your overcurrent relay will not operate here. See, it is having a plug setting value of 0.5 amperes. So it won't operate. But since it is saturated, instead of 10 amperes, it is carrying only 4 amperes. So there is a spill current. See, this is 10 amperes, this is 4 amperes. And there is a spill current. Here, 6 amperes of spill current. So now what is happening? Because of this, the relay is going to operate even though the fault is an external load. And this is happening because of the saturation. Right. See, this is the equivalent circuit which we have gone through. Yeah. See, this is your IA by N. This is your equivalent circuit of CTA, and this is equivalent circuit of CTB. See, this is your primary current referred to the secondary. This is RP dash, which I have already shown you. This is magnetizing circuits. This is what I am representing in the last one. This is I0A, and this is your secondary resistance and load resistance. Okay, and see here also, this is the primary current referred to the secondary for the CTB, and this is primary resistance. This is the magnetizing current, and this is secondary resistance in addition with the load resistance or lead wire resistance, whatever you call it as. Okay, so this is CTB, this is CTA, equivalent circuits. Now both are connected to this P2. This is the point, let us assume. Now this is your saturated CT. Here also the entire current will be flowing into this one, right? This is IC by N, and this is primary side resistance referred to the secondary. This is secondary resistance and load. See here, the magnetizing circuit has been short circuited. This is what we have discussed. For a saturated CT, we assume that the magnetizing circuit has been short circuited. Okay. So now if you carefully see, what is the current which is coming here? This is IA by N. This is the source current if I assume. Now this IA by N, this is the magnetizing current minus I0A. This will be flowing into here, this point, right? IA by N minus I0A. Similarly, IB by N minus I0B, it will be flowing from this point. So these two currents will be added, and this will be the resultant of this IC by N. So whatever the current which you are getting here now, if you carefully see. Now it has two paths. This is one path which it can move. This is the other path which it can move. Otherwise, it will move on to yellow. So two paths are available now. Okay. So see the currents which is coming from your CTA and CTB, they both sum up, and the resultant current has now two parallel paths. One path is through overcurrent relay, the other is through RS plus RL via the short representing the saturated CT. So a part of the fault current now will flow through the overcurrent relay, thereby giving you an alarm, even though the fault is external. So what we should do now, the OC overcurrent relay should not operate for external faults, even though there is a saturation. Right. So what should do? We should limit the current such that it doesn't flow through the overcurrent relay. See, I will draw the circuit here. There were two currents were coming, right? This was IA by N minus I0A. This was IB by N minus I0B. Both currents, they are supposed to flow either to the, this is your overcurrent relay, or So these are of C. Its circuit is shorted, magnetizing circuits. And here I do have RP dash. So whatever the current which I am getting here, the addition of these currents, now it has to flow either through this one or to this one. Right? It has two paths. So now what happens? Since this is an overcurrent relay, since it has paths, so a part of it will surely flow through this one. But assuming that it is having some pickup value of IPU, which is very small, 0.5 amperes normally. See, this is the case. If the current is greater than this one, automatically the relay will give an alarm, which is not desirable. So current must not pass through this one even though it is saturated. This is our target. Understood? So how to not allow this current into this overcurrent relay? What you should do to limit the current in this one? The only option which we do have is nothing but you employ a resistance, high resistance, such that it will limit the current. To what value it must limit the current? It must be less than your pickup value, right? So here you must keep a resistance such that your pickup value current is not exceeded. Your current does not exceed your pickup value, right? And that resistance, see, the above problem can be overcome by connecting a high resistance known as stabilizing resistance, RS. And how it must be chosen? It must be chosen such that the value that under the worst case of maximum external fault and full saturation of 1 CT, the current through the OC relay is less than the pickup value. You don't keep it too high, then internal fault also it will become a problem. Okay, so it must be such that in the worst case of a maximum external fault and full saturation of 1 CT, the current through the OC relay is less than its pickup value. And this type of schemes where you are employing a high impedance or a high resistance in series with your OC relay, these are called as high impedance busbar differential schemes. Understood? So now the question is how to determine the value of stabilizing resistance, here RS, which is to be kept in series with your OC. Now let us suppose the pickup value, it is given by IPU. This is your pickup value of the current. If your current is greater than IPU only, your relay will operate. And your target is to ensure that this current is less than P, pickup value, such that your relay shouldn't operate. So now let the value of resistance associated with the saturated CT. This is of C, CT number C. Right. So this is the CT resistance, and automatically see the impedance of the secondary circuits of the saturated CT. Right. So whatever Z is of CTC is nothing but RS plus RL. Right. Now, as I have already shown you, these are the two currents which are coming, right? This is IA by N minus I naught A. This is IB by N minus I naught B. Now this is one option to go through the overcurrent relay, and this is another option. So this is directly shorted, right? This is RS plus RL. Now your current, either it has to flow through this one or this one. Now let us suppose your overcurrent relay is not connected. Now let us determine what is the voltage at this point. I will take it as V set. Okay, now let us suppose what is the voltage which is across this one. What is the voltage across this one? This is the entire current and this is shorted, right? I will eliminate that there is no current outside this one. So what is V set now? V set is equal to whatever the current which is flowing in this one into the impedance, right? So what is the impedance? It is ZS, which is equal to RS plus RL of your CTC. And what is the current flowing? This is the summation of currents. See, this is the current. Both the currents will be joined. I am just rearranging them. Okay. So this is my V set. If my overcurrent relay was not connected there. So now if I place the overcurrent relay at this particular point, your current must not exceed your pickup value. So you should choose a stabilizing resistance such that it will not allow current I must be less than I pickup value. This condition must be satisfied. So what is this condition now? your this is reset by a stabilizing resistance. It must be right. So which means that at least if it is an equal value. So this is here. Right. So this is here. Now if I assume that there are n number of feeders. Right. So if there are n number of feeders, let us suppose incoming feeders. Okay. And I'll assume that all the magnetization currents, whatever the IA naught and I naught B and I naught C, etc., all are the same, and it is of I naught. And the incoming currents are given by IA by N, IB by N, IC by N. So I'll up to N feeders are there, and all the magnetizing currents I'll take it as I naught. So what is my expression? I'll assume that these are all N incoming feeders, and only total N feeders are there, and out of which only one outgoing feeder is there, and N minus 1 are incoming feeders. In that case, see, this is the summation of currents, right? See, I will show you. Yeah. See, what is Vset? This is Vset, right? See, we have rearranged. These are nothing but your source currents. Refer to the secondary. And these are your summation of your leakage currents. This is what I am trying to write here. This is the currents referred from the primary of those incoming feeders. This is N minus 1 into I naught, leakage currents. I am assuming them to be same, into Zs. What is Zs? Zs is nothing but secondary circuit impedance of your saturated seed. Okay, so this is the maximum external fault current. I'll refer to it as maximum external fault current, which will be flowing into the circuit, right? And this is the entire current which is flowing in the circuit, right? IF external max. So now this is Vset, and we have already seen, right? So what is maximum external fault current, which is to be allowed now, which your relay can detect? It is equal to N into Vset by Zs. This is the maximum external fault current for which your relay can be stable. And what is the stabilizing resistance? To ensure for this one, as I have already given that equation also, your stabilizing resistance must be greater than or equal to your Vset by your I pickup value. Understood? So this is the way how we design a high impedance differential scheme. Okay. So your quick conclusion, yeah, overcurrent relay needs to be restrained from tripping on external faults, even though one of your CT gets completely saturated. This is C. So, and this can be accomplished by connecting a high impedance or high resistance, which we call it as stabilizing resistance, in series with your overcurrent relay. And your stabilizing resistance must be of such a value that even under the worst case of maximum external faults and full saturation of one CT, the current through the overcurrent relay must be less than your pickup value. And these schemes are called as high impedance busbar differential schemes. So I hope that now you are able to describe the need for high impedance busbar protection, and also you are able to design the value of RS, stabilizing resistance. Okay, so this is a theory question. Problems we will discuss in the class, and after that I will give you practice questions again in the class. Thank you for today. And in the next class we will see what is the maximum value of internal fault current for which your relay can stably operate. Okay, thank you. Meet you again in the class.